Warrior 1 and Warrior 2 are just two examples that highlight the importance of space probes in expanding our knowledge of the universe. These spacecrafts provide us with real-time information about our solar system, even if we have been able to study it directly for many years. Recently, the strange data that Voyager 1 has been sending back from deep space has raised questions among NASA engineers about possible unusual messages. Should we be concerned? Let's explore how Voyager 1 has been affected by an unknown force in deep space. For nearly 45 years, the Voyager missions have played a pivotal role in space research, providing some of the first and most consequential observations of our solar system. NASA's twin Voyager spacecrafts are true time capsules from their generation, equipped with an 8-track tape recorder to store data. These recorders have a capacity billions of times smaller than that of today's mobile phones, and they transmit information at speeds up to 38,000 times lower than a modern connection. Yet, these pioneering operations continue to sail beyond the star system, traversing the vast galactic ocean known as space, where no other probe has gone before. These missions are providing a unique picture of the interactions between the heliosphere and interstellar space. Scientists are comparing data from the probe's first missions with more recent observations. No other spacecraft has transformed our understanding of the Sun and its impact on the space environment like the Voyagers have. Each spacecraft also acts as an ambassador for humanity, carrying a gold record with musical recordings, greetings in different languages, images of life on Earth, and diagrams of basic scientific principles intended for whoever might encounter these probes. The gold coating on the records acts as a cosmic message in a bottle, as its resistance to corrosion in space will allow the information they contain to remain intact for more than 1 billion years. Experts are surprised by the strength and direction of the interstellar magnetic field, which has sparked debates about the shape and behavior of the heliosphere, the magnetic region dominated by the Sun. The heliosphere was long thought to be comet-shaped, but it is now thought to be more spherical than previously assumed. One question is whether the heliosphere expands and contracts in response to the appearance and disappearance of sunspots, or whether it remains relatively constant. The spacecraft have provided intriguing clues to this question. Astronomers suggest that the interstellar medium begins when the solar wind, the stream of charged particles from the Sun, dries up. This plasma, or ionized gas, interacts with a cooler, denser interstellar plasma, much like a stone thrown into a stream. Similar to the way the Earth's troposphere has a boundary layer called the tropopause, the heliosphere has its own boundary, known as the heliopause, which is shaped by the Sun. The exact distance of the heliopause was a mystery when the Voyager probes were launched. Although Jupiter is only 5 times the distance between Earth and the Sun, some thought the heliopause might be close by. However, estimates of this distance increased as the spacecraft traveled farther and farther away. It wasn't at Jupiter, Saturn, Uranus, or Neptune that marked Voyager's entry into interstellar space. The probe detected signals from the heliopause shortly after its encounter with Neptune in July 1992. Both probes began recording powerful radio signals at frequencies of about 2 to 3 kilohertz. Some scientists believe these radio waves were related to 6 large solar flares that occurred more than a year before they were detected. Plasma ejected during these flares reached the heliopause, causing electrons to vibrate and emit radio waves. Although these signals were too weak to be detected on Earth, the interstellar medium is much denser than the outer regions of the heliosphere. The distance to the heliopause was determined by measuring the speed of solar material and the time it took to reach that boundary, a distance that varies between 116 and 177 astronomical units. On August 25, 2012, at a distance of 121.6 astronomical units, Voyager 1 crossed the heliopause. There were clear signs that it had crossed this boundary, such as the disappearance of high-energy particles from the solar wind, indicating that the rest of the solar wind had also been left behind. In addition, cosmic rays from outer space, which are partly blocked by the heliosphere, increased significantly after Voyager's crossing. However, not all scientists were immediately convinced. Voyager 1's plasma instrument had stopped working, which prevented it from recording the dramatic increase in particle density that occurs when leaving the heliosphere and entering interstellar space. In addition, the magnetic field beyond the heliosphere was expected to have a different direction, but that did not happen. The similarity in the orientation of the magnetic fields inside and outside the heliosphere remains without a clear explanation. The Sun also plays a role in this discovery. In early 2012, solar storms began to occur, and the following year, these disturbances shook the plasma that Voyager 1 was passing through. As a result, electrons in the plasma began to oscillate, generating radio waves that the spacecraft could detect. These waves indicated that Voyager had entered a much denser region. In 2018, Voyager 2 also crossed the heliopause on November 5th. This time, there was no doubt. The spacecraft's plasma instrument was working properly and recorded the increase in the density of particles, such as protons, electrons, and other charged particles. It also measured the temperature, which ranged from 30,000 to 50,000 Kelvin, much higher than that of the interstellar medium. The plasma was probably compressed as it entered the heliosphere, which explains what happened. As in the case of Voyager 1, the probe observed a decrease in the solar wind and an increase in cosmic rays coming from outside the solar system. However, the magnetic field did not change in direction, confirming that the result observed 6 years earlier was no exception. The relatively close distances suggest that the heliopause is stronger than previously thought. Both Voyager 1 and 2 probes are still moving away from the heliosphere, the exact shape of which is still unclear. Since the signals they send travel at the speed of light, it takes more than 22 hours for them to reach Earth. By the end of 2023, when Pioneer 10 finally stops operating, Voyager 2 will have traveled 129 astronomical units, marking it as the second farthest spacecraft ever launched. Both probes are traveling in opposite directions and are farther from Earth than any other spacecraft. Scientists reported that Voyager 1 had detected a hump related to waves in localized regions of gas in the early empty space between stars. As the probe's plutonium degrades and generates less heat, NASA has reported that to compensate, the team has disabled several systems, including some initially considered essential, such as the heaters that protect instruments from the cold of space. Remarkably, all 5 devices whose heaters were turned off in 2019 are still operating. The Voyager's longevity at much lower temperatures than anticipated remains a mystery to NASA scientists. In 2022, Voyager's attitude control and articulation system experienced a failure. The system is crucial to keeping the antennas pointed toward Earth. Prior to this failure, the probe's performance had been flawless, but the craft began sending incorrect telemetry data due to a malfunction in an onboard computer that had stopped working years earlier. This confused the craft and disrupted its ability to determine its orientation. However, NASA engineers managed to solve the problem by having the system reset using an older computer. Despite this success, some are wondering if the time has come to retire the Voyagers, the oldest and most distant spacecraft. Although the mission remains viable, several scientists are already exploring the possibility of developing successors to the Voyagers. No one knows for sure how long these probes, which rely on plutonium to generate heat and keep the fuel that lines up the antennas toward Earth from freezing, will continue to operate. Over time, plutonium degrades, producing less power each year. Let me know what you think in the comments box. If you enjoyed the video, don't forget to give it a like and subscribe. Then, I'll be seeing you in the next video.